Okay, hello Internet. Let's pick up where we left off, which is, I'm going to do some cleanup first. I'm going to commit some git changes like this. We'll just call it an initial commit. So then when I write in the changes from this next section of the instructions, then I'll be able to view clearly what was changed. Should be good. Okay. Generating a random number. This is where we left off, right? Yeah, we left off with this comment about cargo and its ecosystem. Generating a random number. Let's start using rand to generate a number to guess. The next step is to update source/main.rs as shown in listing 2-3. So we'll go vim main/routes vim source/main.rs. Good deal. We're gonna add use rand ::rng semicolon. Then we have this additional line, let secret number, and notice we haven't called mut for mutable because this secret number isn't going to change during the life of the program. Rand : thread rng dot gen range 1 ... equal 100. Interesting syntax there. And the rest of that looks the same. Let's write that just for now. Listing 2-3, adding code to generate a random number. First we add the line use rand : rng. The rng trait defines methods that random number generators implement, and this trait must be in scope for us to use those methods. Chapter 10 will cover traits in detail. That's good because I don't know what a trait is. Next, we're adding two lines in the middle. In the first line, we call the rand : thread rng function that gives us the particular random number generator that we're going to use, one that is local to the current thread of execution and seeded by the operating system. Then we call the genRange method on the random number generator. So thread rng creates a random number generator, and genRange uses it to give us a random number. The kind of range expression we're using here takes the form start ... equal end, and is inclusive on the lower and upper bounds, so we need to specify 1 ... equal 100 to request a number between 1 and 100. Note, you won't just know which traits to use and which methods and functions to call from a crate, so each crate has documentation with instructions for using it. Another neat feature of cargo is that running the cargo doc -- open command will build documentation provided by all of your dependencies locally and open it in your browser. That's nice. If you're interested in other functionality in the rand crate, for example, run cargo doc open and click rand in the sidebar on the left. Let's give that a try. Cargo doc open. Oh, we gotta build stuff. Let's look at rand. Utilities for random number generation. Rand provides utilities to generate random numbers, to convert them to useful types and distributions, and some randomness-related algorithms. That's nice. Oh, there's a whole book. Wow. Okay. Well, that's neat. I don't remember when I opened this, so we'll just ignore it for now. The second new line prints the secret number. Oh, I missed that line. I guess I better go back. Println, the secret number is, yeah, sure enough, I missed that. So let's go back to Vim source main. So after let secret number, we have print ln exclamation point, and the exclamation point means the macro. Quote, the secret number is colon, curly brace, secret number, and then end paren and semicolon. Okay. The second new line prints the secret number. This is useful while we're developing the program to be able to test it, but we'll delete it from the final version. It's not much of a game if the program prints the answer as soon as it starts. Try running the program a few times. Alright. Cargo run. Secret number is 50. Please input your guess. I'll say 3, pretending I don't know. You guessed 3, and that's the end of the program. Let's do that again. Cargo run. The secret number is 51. I'm going to go ahead and guess 50. You should get different random numbers, and they should all be numbers between 1 and 100. It's funny how I got 2 next to each other. Let's just be sure that it's not going to do that a third time. 94, okay. And this time, just for fun, I'm going to guess 94. Comparing the guess, did I read that? Yeah. Comparing the guess to the secret number. Let's now look at get diff and review what changed. We have those extra added lines. One with let secret number, one with println secret number, and one with use rand. Now I think someone said you can just do cargo fmt and it'll format things for you. Let's see if that made a difference. Looks like it moved things around a little bit. So it did do something. Okay. Neat. Now I remember this image. I think this means that, it tells me right there. This code does not compile. I wonder why. Now that we have a user input and a random number, we can compare them. That step is shown in listing 2-4. Note that this code won't compile quite yet, as we will explain. File name source main.rs. Well, let's first git add -u. I'm trying. A colleague told me I can use -u instead of add dot, and it's less aggressive. In case there's stuff that you don't want to be included in the thing. Anyway, git commit generate secret number right quit. Okay, then main.rs. Oops. Source/main.rs. Println you guessed guess, so we start right there. Match. Oh, I need to use std cmp ordering semicolon. Match and guess.cmp. This is an interesting way of doing things. At secret underscore number, close paren, brace, ordering, less, arrow, print ln, exclamation point, quotes, too small. Ordering, greater, arrow, print, ln, exclamation point, too big. Ordering, equal, print, ln, exclamation point, quote, you win. And there should be a comma after every one of those. Close that brace. And let's watch this hilariously fail to compile. Okay, compiling guessing game error E308, mismatched types in source main.rs 2221. Match guess.cmp at secret number. Bunch of angry little carrots saying expected struct string found integer. Arguments to this function are incorrect. Note, expected reference at string found reference at curly brace integer. Note, associated function definition. Associated function defined here. For more information about this error, try rustc-ex plain E0308. Let's try that. Error could not compile guessing game due to previous error. Rustc-explain E308. What? Oh, this is less. Expected type did not match the received type. Erroneous code examples. Interesting. Okay, let's see what the book has to say about this, though. Listing 2.4 at handling the possible return values of comparing two numbers. First, we had another use statement. Oh yeah, let's see our git diff. Oh, this is warning me that there's blank spaces there. I guess those don't need to be there. But we added standard CMP ordering, and we used .cmp. I guess that makes it feel like CMP and ordering live in the same namespace. They're both made available because we typed .cmp here and we typed ordering here. Interesting, huh? So you have to be careful about what you name things. That seems like it could be a problem. We'll see if it comes up. Okay, first we had another use statement bringing a type called std cmp ordering into scope from the standard library. The ordering type is another enum and has the variants less, greater, and equal. These are the three outcomes that are possible when you compare two values. Then we add 5 new lines at the bottom that use the ordering type. The CMP method compares two values and can be called on anything that can be compared. It takes a reference to whatever you want to compare with. Here it's comparing the guess to the secret number. Comparing, let's go back to vim source/main.rs. Guess.cmp secret number. So it's comparing guess with secret number. The CMP method matches two values and can be called on anything that can a secret number. Then it returns a variant of the ordering enum we brought into scope with the use statement. We use a match expression to decide what to do based on the next value of the based on which variant of ordering was returned from the call to CMP with the values in guess and secret number. Okay. So we're matching ordering : less, or we're matching or greater, or we're matching equal. And these are the different possible enum values of the ordering enum. A match expression is made up of arms. An arm consists of a pattern to match against and the code that should be run if the value given to match fits that arm's pattern. Rust takes the value given to match and looks through each arm's pattern in turn. Patterns in the match construct are powerful Rust features that let you express a variety of situations your code might encounter and make sure that you handle them all. These features will be covered in detail in Chapter 6 and Chapter 18, respectively. Patterns and the match construct. Okay. Let's walk through an example with the match expression we have here. Say that the user has guessed 50 and the randomly generated secret number this time is 38. When the code compares 50 to 38, the CMP method will return ordering : greater because 50 is greater than 38. The match expression gets the ordering greater value and starts checking each arm's pattern. It looks at the first arm's pattern, ordering less, and sees that the value ordering greater does not match ordering less, so it ignores the code in that arm and moves to the next arm. The next arm's pattern is ordering greater, which does match ordering greater. The associated code in that arm will execute and print too big to the screen. The match expression ends after the first successful match, so it won't look at the last arm in this scenario. However, the code in listing 2-4 won't compile yet. Let's try it. And here's expected struct string found integer. The core of the error states that there are mismatched types. Rust has a strong static type system. However, it also has type inheritance. When we wrote let mute guess equals string new, Rust was able to infer that guess should be a string and didn't make us write the type. Oh, type inference. Yeah, okay. The secret number, on the other hand, is a number type. A few of Rust's number types can have a value between 1 and 100. I32, a 32-bit number, U32, an unsigned 32-bit number, I64, a 64-bit number, as well as others. Unless otherwise specified, Rust defaults to an I32, a 32-bit number, with a sign. Defaults to an I32, which is the type secret number, unless you add additional information to Elbow that would cause Rust to infer a different numerical type. The reason for the error is that Rust cannot compare a string and a number type. Ultimately, we want to convert the string the program reads as an input into a real number type so we can compare it numerically to the secret number. We do this by adding this line to the main function body. Before we do that, let's quit here. Again, let's do cargo format. Now let's look at git diff. It took away that extra white space that it was complaining about before. Let me be clear there. Cargo FMT took away the white space that Git had been complaining about before. Interesting that it chooses. Let's look again. Or let's look within Vim. There's nothing on this line, so it ends here. Just an interesting. Oops. Pushed the wrong button in the wrong order. File. Snip. Ultimately, we want to convert the string the program reads as an input into a real number type so we can compare it numerically to the secret number. We do so by adding this line to the main function body. Okay, then source /rs. So after we have let mute guess equals string new IO_std in, then we're adding this line, let guess colon u32. Now this is already interesting because we had a mutable guess up here, but now we have let guess, which is going to be immutable, but it uses the same name. That seems really strange to me, but let's see how it goes. Guess equal guess.trim parens.parse parens.expect quote, and I remember from before that expect is what will happen in the case of an error. Please type a number, end parens semicolon. The line is let guess u32 equal guess.trim.parse.expect. Please type a number. We create a variable named guess, but wait, doesn't the program already have a variable named guess? It does, but helpfully Rust allows us to shadow the previous value of guess with a new one. Shadowing lets us reuse the guess variable name rather than forcing us to create two unique variables, such as guess string and guess, for example. We'll cover this in more detail in Chapter 3, but for now, know that this feature is often used when you want to convert a value from one type to another type. I'm not sure how I feel about this one, because it's convenient that you can use the name guess both times, but it's potentially confusing if you don't remember which type you're dealing with on a given line. So I don't know how I feel about that. We bind this new variable expression to the guess.trim.parse. We bind this new variable to the expression guess.trim.parse. The guess in the expression refers to the original guess variable that contained the input as the string. The trim method on a string instance will eliminate any white space at the beginning and end, which we must do to be able to compare the string to u32, which can only contain numerical data. The user must press enter to satisfy read line, and their input guess, which adds a new line character to the string. For example, if a user types 5 and presses enter, guess looks like this, 5/n. The /n represents a new line. On Windows, pressing enter results in a carriage return and a new line, /r/n. The trim method eliminates /n or /r/n, resulting in just 5. Danny McGee over on Twitch says, "Hello, how is the Rust?" It's going okay. So far, the book is nice and clear and understandable. What is this 19 icon? Oh, probably TwitchCon 19. The parse method on strings converts a string to another type. Here we use it to convert from a string to a number. We need to tell Rust the exact number type that we want by using let guess. Okay, let's pull up the line in question. Here it is. Let guess colon u32. The colon after guess tells Rust will annotate the variable's type. Rust has a few built-in numbers types. The u32 seen here is an unsigned 32-bit integer. It's a good default choice for a small positive number. You'll learn about other number types in Chapter 3. Additionally, the u32 annotation in this example program and the comparison with secret number means that Rust will infer that secret number should be a u32 as well. Now the comparison will be between two values of the same type. Well, that's kind of clever. The parse method will only... Oh, yeah, I did that. What am I saying? The parse method will only work on characters that can logically be converted into numbers and so can easily cause errors. If, for example, the string contained a thumbs up emoji, %, there would be no way to convert that to a number. Because it might fail, the parse method returns a result type, much as the readline method does discussed earlier in handling potential failures with the result type. We'll treat this result in the same way by using the expect method again. If parse returns an ERR result variant because it couldn't create a number from the string, the expect call will crash the game and print the message we give it. If parse can successfully convert the string to a number, it will return the OK variant of the result, and expect will return the number that we want from the OK value. Okay, let's run the program now. Cargo run. I'm gonna guess 10. You guessed 10. Too big. Hey, it worked. And they did it with some spaces there before 76. So it's nice. Even though spaces were added before the guess, the program still figured out that the user guessed 76. Run the program a few times to verify the different behavior with different kinds of input. Guess the number correctly, guess a number that is too high, and guess a number that is too low. Alright, we can verify these things. Let's see, we were too big, so let's use 21 now. Too small. Cargo run. Oh, it ran much more quickly that time. Let's go ahead and guess 51. You guessed 51. You win. However, I still want to try it with an invalid entry. Huh, it's kind of verbose what it gave me. Thread main panicked at, oh, it panicked. Interesting. At please type a number, parse int error, kind invalid digit, source main rs2043, note run with rust backtrace equal 1 environment variable to display a backtrace. Not gonna worry about that for now. The point is it works. Let's get add dot, get status, make sure I didn't add anything extra. Cool. Add comparisons. Cool. We have most of the game working now, but the user can only make one guess. Let's change that by adding a loop, allowing multiple guesses with looping. The loop keyword creates an infinite loop. We'll add a loop to give users more chances of guessing the number. So, them main slash, them source, what the heck? Them c slash main rs. Okay. So followed by the secret number, following the secret number is, we're adding a loop. Okay, there we go, that's better. Loop, braces, and we're adding in extra I won't bother with all the formatting myself. This is where cargo format, I think, is really going to shine. So all we did was create an infinite loop. So if we look at git diff, we see the lines that I changed. But now let's do cargo fmt and check out the git diff. We have a lot of things that change their indentation. And let's look at vim source/main.rs. And it looks nice and clean and formatted. That's good. As you can see, we've moved everything from the guess input prompt onward into a loop. Be sure to indent the lines inside the loop, another 4 spaces each, and run the program again. The program will now ask for another guess forever, which actually introduces a new problem. It doesn't seem like the user can quit. Okay, let's go run. Let's enter 86. You win. Please enter your guess. Oh, I'll try 87. Too big. Please input your guess. Oh, I'll try 85. Too small. Please insert your guess. Try 86 again. You win, but it still says insert your guess. Input your guess. So, okay, the user could always interrupt the program by using the keyboard shortcut Control-C. I'll do that now. Oh, and it just exits. Okay. Exits quietly. But there's another way to escape this insatiable monster, as mentioned in the parse discussion in comparison the guess to a secret number. If the user enters a non-number answer, the program will crash. We can take advantage of that to allow the user to quit, as shown here. Oh, you can enter a guess of quit. That's clever. Please type a number. Cool. Typing quit will quit the game, but as you'll notice, so will entering any other non-number input. This is suboptimal to say the least. We want the game to also stop when the correct number is guessed. Let's program the game to quit when the user wins by adding a break statement. Okay, we'll go back to vim source main.rs, and on this match thing, we go on the line that has ordering equal. Instead of doing this on one line, we get a brace. We have a... Interesting, we don't have a comma anymore, we have a semicolon. Oops. Break semicolon. And then closing brace. I think I got the format right, but let's just try cargo fmt. I'm gonna git diff. Oh, I didn't commit any of the... Oh, well. So be it. Add loop. Adding the break line after you win makes the program exit the loop when the user guesses the secret number correctly. Exiting the loop also means exiting the program because the loop is the last part of main. Let's convince ourselves of that fact. Vim source/main.rs. Loop is here, and that's the... There's the brace that closes the loop, so sure enough, that's the last thing in main. Okay, handling invalid input. To further refine the game's behavior, rather than crashing the program when the user inputs a non-number, let's make the game ignore a non-number so the user can continue guessing. We can do that by altering the line where guess is converted from a string to a U32, as shown in listing 2.5. Okay, so instead of just an expect, we have a match statement. We'll go back to this. Let guess equal U32. Let guess U32 equal match guess.trim.parse. And then in place of the .expect, we have what's happening. If it's okay, number, go to number. If it's error of whatever. So it looks like we're not using whatever the error is. Oops. Oh no, what did I do? I need to go to Vim Gem. I can get rid of, please type a number. Error goes to whoa. It's trying to be clever with the formatting and it's not doing what I like. We'll just let it. Error. Continue, comma, new line, close the curly brace, semicolon. And let's cargo format. Looks about the same. Okay. But we still haven't dealt with how to quit now. Well, let's just play with it. Cargo run. Secret number is 23. Please input your guess. 1, too small. 88, too big. 23, you win. Oh, and it exits. Well, okay, let's run again. Secret number is 75. Please input your guess. Let's guess 74. And I give up. And it just continues on and asks for another guess. What if I do quit? Please input your guess. So this isn't quite the behavior we want. Well, let's Control C out of that. Get, where are we now? Get commit. Get add bot, get commit. Continue on invalid input. We switch from an expect call to a match expression to move from crashing on an error to handling the error. Remember that parse returns a result type, and result is an enum that has the variants OK and ERR. We're using a match expression here as we did with the ordering result of the CMP method. If parse is able to successfully turn the string into a number, it will return an OK value that contains the resulting number. The OK value will match the first arm's pattern, and the match expression will just return the number value that parse produced and put inside the OK value. that number will end up right where we want it in the new guess variable we're creating. All right, let's look at this code. In the case that it's okay, I wonder why we need the num in parentheses though. If parse is not able to turn the string into a number, it will return an ERR value that contains more information about the error. The error value does not match the OK num pattern in the first match arm, but it does match the ERR for an underscore pattern in the second arm. The underscore is a catch-all value. In this example, we're saying we want to match all ERR values no matter what information they have inside of them. So the program will execute the second arm's code continue, which tells the program to go into the next iteration of the loop and ask for another guess. So, effectively, the program ignores all errors that parse might encounter. Now everything in the program should work as expected. Let's try it. Cargo run, guess the number. The secret number is 61. Please input your guess 10, too small. Please input your guess 99, too big. Please input your guess foo. Please input your guess 61, you win. Awesome. With one tiny final tweak, we will finish the guessing game. Recall that the program is still printing the secret number. That worked well for testing, but it ruins the game. Let's delete the println that outputs the secret number. Listening 26 shows the final code. Let's go into here, and we'll delete that line and the line below it. Yep, get commit -a for adding. Remove debug. Look. Guessing 2.6 complete guessing code game. Summary: at this point, you've successfully built the guessing game. Congratulations. This project was a hands-on way to introduce you to many new Rust concepts. Let, match, functions, the use of external crates, and more. In the next few chapters, you'll learn about these concepts in more detail. Chapter 3 covers concepts that most programming languages have, such as variables, data types, functions, and shows how to use them in Rust. Chapter 4 explores ownership, a feature that makes Rust different from other languages. Chapter 5 discusses structs and method syntax. And Chapter 6 explains how enums work. Let's play this game. Cargo run. Guess the number. I don't know what the number is. I'll say 50. Too big. Let's try 25. Too big. 12. Too big. Let's try 1. Too small. 5. Oh! You win. Cool. However, I kind of want to be able to say quit and have that. How would I do that? If I wanted to be able to type quit and it would exit the game without making me win. I'm not sure, but this Pomodoro timer has long since gone. So it's time to go to the BRB screen. All right. Getting into this third chapter. Common programming concepts. This chapter covers concepts that appear in almost every programming language and how they work in Rust. Many programming languages have much in common at their core. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust and explain the conventions around using these concepts. Specifically, you'll learn about variables, basic types, functions, comments, and control flow. These foundations will be in every Rust program, and learning them early will give you a strong core to start from. Keywords. The Rust language has a set of keywords that are reserved for use by the language only, much as in other languages. Keep in mind that you cannot use these words as names of variables or functions. Most of the keywords have special meanings, and you'll be using them to do various tasks in your Rust programs. A few have no current functionality associated with them, but have been reserved for functionality that might be added to Rust in the future. You can find a list of the keywords in Appendix A. I'll just let myself discover the keywords as we come to them. Variables and mutability. As mentioned in the Storing Values with Variables section, by default, variables are immutable. This is one of the many nudges Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. However, you still have the option to make your variables mutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, once a value is bound to a name, you can't change that value. To illustrate this, let's generate a new project called Variables in your projects directory by using cargo new variables. Alright, going to the projects directory. Cargo new variables. CD variables. We've got some untracked files including .gitignore, cargo.toml, and source. What do we have here? Nothing. Okay. Let's vim src/main.rs. We can delete what's here. Start in with fn main parens brace. Let x equal 5. Print ln exclamation point quote value of x is colon brace x quote parens semicolon. Now we say x equals 6, which the compiler is not going to like. Print ln exclamation point the value of x is x. Save and run the program using cargo run. First assignment to X, help consider making this binding mutable. Carrots cannot assign twice to immutable variable. I like how you can do rust c explain. I might make a series of videos just doing the rust c explains on various errors. That might be interesting. You should receive an error message as shown in this output. This example shows how the compiler helps you find errors in your programs. Compiler errors can be frustrating, but really they only mean your program isn't safely doing what you want it to do yet. They do not mean that you're not a good programmer. Experienced rustaceans still get compiler errors. Okay. The error message indicates that the cause of the error is that you cannot assign twice to immutable variable x, because you tried to assign a second value to the immutable x variable. It's important that we get compile time errors when we attempt to change a value that's designated as immutable, because this very situation can lead to bugs. If one part of our code operates on the assumption that a value will never change, and another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to do. The cause of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. The Rust compiler guarantees that when you state a value won't change, it really won't change, so you don't have to keep track of it yourself. Your code is thus easier to reason through. But mutability can be very useful and can make code more convenient to write. Although variables are immutable by default, you can make them mutable by adding mut in front of the variable name as you did in Chapter 2. Adding mut also conveys intent to the future readers of the code by indicating that other parts of the code will be changing this variable's value. For example, let's change src/main.rs to the following. So here goes vim again, let x, let mut x, 5, cargo run. We're allowed to change the value bound to x from 5 to 6 when mut is used. Ultimately, deciding whether to use mutability or not is up to you and depends on what you think is clearest in that particular situation. Constants. Like immutable variables, constants are values that are bound to a name and are not allowed to change, but there are a few differences between constants and variables. First, you aren't allowed to use mut with constants. Constants aren't just immutable by default, they're always immutable. You can declare constants using the const keyword instead of the let keyword, and the type of the value must be annotated. We're about to cover types and type annotations in the next section, data types, so don't worry about the details right now. Just know that you must always annotate the type. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code need to know about. The last difference is that constants may be set only to a constant expression, not the result of a value that could be computed at runtime. That could only be computed at runtime. Here's an example of a constant declaration. Const 3 hours in seconds, U32 equals 60 times 60 times 3, semicolon. The constant's name is 3 hours in seconds, and its value is set to the result of multiplying 60, the number of seconds in a minute, by 60, the number of minutes in an hour, by 3, the number of hours we want to count in this program. Rust's naming convention for constants is to use all uppercase with underscores between words. The compiler is able to evaluate a limited set of operations at compile time, which lets us write out this value in a way that's easier to understand and verify, rather than setting this constant to the value 10,800. See the Rust references section on constant evaluation for more information on what operations can be used when declaring constants. Well, just as a start, I assume you can't use a mutable variable inside of the constant. Constants are valid for the entire time a program runs within the scope they were declared in. This property makes constants useful for values in your application domain that multiple parts of the program might need to know about, such as the maximum number of points any player of a game is allowed to earn or the speed of light. Naming hard-coded values throughout your program as constants is useful in conveying the meaning of that value to future maintainers of the code. It also helps to have only one place in your code, and you would need to change if the hard-coded value needed to be updated in the future. Shadowing. Let's commit this bit. Do I care? Yeah, let's commit it. Oh, this is actually the initial commit. Mutable variable. I don't know if I'll ever go back to this Git history, but I feel good about having it. Shadowing. As you saw in the guessing game tutorial in chapter 2, you can declare a new variable with the same name as the previous variable. Restorations say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any uses of the variable name to itself until either it is overshadowed or the scope ends. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. Oh, interesting. I see what they're doing. I think I see what they're doing here. Anyway, vim certs main.rs fn. I didn't need to delete that first line. Oh well. Let x equal 5 semicolon. Let x equal x plus 1. And then I kind of want to print now, but I'll stick to the example. Let x equal x times 2. It's a little mind-bending, I think. Println exclamation point, quote, the value of x in the inner scope is colon, braces, x brace, quote, paren, semicolon. Okay, and then we close that scope. Now, println exclamation point, quote, the value of x is colon, brace x, end quote, and paren, semicolon, and the final brace. Let's stop and think about what this would do. We have let x equal 5. If we printed it now, we would get 5. We have let x equal x plus 1. So over here we have x equals 6. But here we have let x equal x times 2, so 12. The value of x in the inner scope is 12, but now we come back, the value of the x is, and I think it's going to be 6 again, because it said it only applies through the end of its scope. So so this x shadows the other overshadows the other x, but doesn't destroy it, because this x is still valid in its scope. That's kind of how I'm thinking this should work. Quit. Let's just run it and see what we get. The value of x in the inner scope is 12. The value of x is 6. Cool. Okay, now on to the commentary in the program first binds x to a value of 5. Then it creates a new variable x by repeating let x equal, taking the original value and adding 1 so that the value of x is then 6. Then, within an inner scope created with the curly brackets, the third let statement also shadows x and creates a new variable, multiplying the previous value by 2 to give x a value of 12. When that scope is over, the inner shadowing ends and x returns to being 6. When we run this program, it will output the following: cargo run, compiling for variables v0 point, whatever, finished, running. The value of x in the inner scope is 12, the value of x is 6. Shadowing is different from marking a variable as mutable, because we'll get a compile time error if we accidentally try to reassign this variable without using the let keyword. By using let, we can perform a few transformations on a value, but have the variable be immutable after those transformations have been computed. That is interesting. The other difference between mute and shadowing is that because we're effectively creating a new variable, when we use the let keyword again, we can change the type of the value but reuse the same name. For example, say our program asks the user to show how many spaces they want between some text by inputting some space characters, and then we want to store that input as a number. So let spaces equal quote, space, 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 quote, let spaces equal spaces.len paren. The first spaces variable is a string type, and the second spaces variable is a number type. Shadowing thus spares us from having to come up with different names such as spaces string and spaces num. Instead, we can reuse the simpler spaces name. However, if we try to use mute for this as shown, we get a compile time error. This code does not compile. Let mute spaces equal quote space 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 quote spaces equal spaces.lang. Now what is the error going to be? I kind of want to do it in mind so that I can git commit -a. What was this one about? Shadowing. Get kind of jazzy on this one. I like it. The music, background music that is. Okay, vim source/main.rs. Let mut spaces equals quote space 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 quote semicolon spaces equals spaces.lang. Right quit, cargo run. Expected string found usize. What? Mismatched types. Expected at string found usize. What is usize? Expected pointer to string found usize. Alright, let's rust usize. Usize, the pointer sized unsigned integer type. Oh. It's a pointer to an integer. I'll just move forward from that and let it explain that to me later. Data types. Every value in Rust is a certain data type, which tells Rust what kind of data is being specified so it knows how to work with the data. We'll look at two data type subsets, scalar and compound. Keep in mind that Rust is a statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want to use based on the value and how we use it. In cases when many types are possible, such as when we converted a string to a numeric type using parse, in the comparing the guess to the secret number section in chapter 2, we must add a type annotation like this. Let guess :u32 equal quote 42.parse.expect not a number. If we don't add the u32 type annotation above, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. Consider giving guess a type. Compiling no type annotations v0.1.0. Type annotations needed. You'll see different type annotations for other data types. Scalar types. A scalar type represents a single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Integer types. An integer is a number without a fractional component. We used one integer type in Chapter 2, the U32 type. This type declaration indicates that the value it's associated with should be an unsigned integer. Signed integers types start with I instead of U. That takes up 32 bits of space. Table 3-1 shows the built-in integer types in Rust. We can use any of these variants to declare the type of an integer value. Table 3-1 integer types in Rust: 8-bit, 16-bit, 32-bit, 64-bit, 128-bit, and arch. What is arch? So it's I8, U8, I32, U32, and so on, I size and U size. Each variant can either be signed or unsigned and has an explicit size. Signed and unsigned refers to whether it's possible for the number to be negative. In other words, whether the number needs to have a sign with it signed, or whether it will only ever be positive and can therefore be represented without a sign. Unsigned. It's like writing numbers on paper. When the sign matters, a number is shown with a plus sign or a minus sign. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored using 2's complement representation. What would that take us? Do I want to go on that wiki walk? Not right now. I'll open it in case I decide to do it later. Each signed variant can store numbers from -2 to the n minus 1 to 2 to the n minus 1 minus 1 inclusive, where n is the number of bits that the variant uses. So an I8 can store numbers from -2 to the 7 to 2 to the 7 minus 1, which equals -128 to 127. Unsigned variants can store numbers from 0 to 2n minus 1. So an U8 can store numbers from 2 to 2 to the 8 minus 1, which equals 0 to 255. Yeah, binary. Additionally, the I size and U size types depend on the architecture of the computer your program is running on, which is denoted in the table as arch. 64 bits if you're on a 64-bit architecture, and 32 bits if you're on a 32-bit architecture. Okay, that's the arch thing. You can write integer literals in any of the forms shown in Table 3-2. Table 3-2, integer literals in Rust. Note that number literals can be multiple numeric types. Note that number literals that can be multiple numeric types allow a type suffix, such as 57U8 to designate the type. Number literals can also use underscore as a visual separator to make the number easier to read, such as 1_000, which will have the same result if you had specified 1000. Table 3-2, integer literals in Rust. Decimal, hex, 0xFF, octal, 0077, binary, 0B1111_0000, byte, U8 only, B quote A. So how do you know which type of integer to use? If you're unsure, Rust defaults are generally good places to start. Integer types default to I32. The primary situation in which you'd use I size or U size is when indexing some sort of collection. Okay, a little bit about integer overflow. Let's say you have a variable of type U8 that can hold values between 0 and 255. If you try to change the variable to a value outside that range, such as 256, integer overflow will occur, which results in one of two behaviors. When you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime if this behavior occurs. Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth in Unrecoverable Errors with Panic section in Chapter 9. When you're compiling in release mode with the release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs 2's complement wrapping. In short, values greater than the maximum value the type can hold wrap around to the minimum of the value the type can hold. In the case of a U8, the 256 becomes 0, the value 257 becomes 1, and so on. The program won't panic, but the variable will have a value that probably isn't what you were expecting it to have. Relying on integer overflows wrapping behavior is considered an error. To explicitly handle the possibility of an overflow, you can use these families of methods provided by the standard library for primitive numeric types. Wrap in all modes with the wrapping methods, such as wrapping add. Return the none value if there is an overflowing with the checked star methods. Return the value and a boolean indicating whether there was an overflow with the overflowing _star methods. And saturate at the value's maximum or minimum values with saturating methods. So, such as wrapping add. So instead of just add method, wrapping add. So you could do checked _ add, or overflowing add, or interesting. Okay, moving on. Floating point types. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust floating point types are F32 and F64, which are 32 bits and 64 bits in size respectively. The default type is F64 because on modern CPUs, it's roughly the same speed as F32 but capable of more precision. All floating point types are signed. Here's an example that shows a floating point number in action. Function main, let x equal 2.0, let y colon F32 equal 3.0. X would have been F64. Floating point numbers are represented according to the IEEE 754 standard. The F32 type is a single precision float, and F64 has double precision. Number operations. Rust supports the basic mathematical operations you'd expect for all of the number types: addition, subtraction, multiplication, division, and remainder. Integer division rounds down to the nearest integer. Following code shows how you'd use each numeric operator in a let statement. It's interesting that it allows me to run this. It's not going to really do anything. Function main, let sum equal 5 plus 10 addition. Subtraction, let difference equals 95.5 minus 4.3. Multiplication, let product equal 4 times 30. Let quotient equal 56.6 divide 32.2. And let floor equal 2 divided by 3 results in 0. And let remainder equals 43% 5. Each expression in these statements uses a mathematical operator and evaluates to a single value, which is then bound to a variable. Appendix B covers a list of all operators that Rust provides. Okay. The Boolean type. As in most other programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. 1 byte. Isn't a byte 8 bits? Why would it take up a whole byte? Anyway, the Boolean type in Rust is specified using bool. For example, let main, function main, let t equal true, let f colon bool equal false with explicit type annotation. I'm kind of stuck on this byte thing. Anyway, the main way to use Boolean values is through conditionals, such as an if expression. We'll cover how if expressions work in Rust in the control flow section. The character type. Rust's char type is the language's most primitive alphabetic type. Here's some examples of declaring char values. In function main, let C equal single quote letter Z, let Z colon char equal, and it's this fancy Z from, Unicode something or other with explicit type annotation, and let hard-eyed cat equal quote and the hard-eyed cat emoji and the quote. Note that we specify char literals with single quotes as opposed to string literals which use double quotes. Rust's char type is 4 bytes in size and represents a Unicode scalar value, which means it can represent a lot more than just ASCII. ASCII, I guess. Oh, I'm getting tired. Accented letters, Chinese, Japanese, and Korean characters, emoji, and zero-width spaces are all valid char values in Rust. Unicode scalar values range from U plus 000 to U plus D7FF, and U plus E000 to U plus 10FFFF inclusive. However, a character isn't really a concept in Unicode, so your human intuition for what a character is may not match up with what a char is in Rust. We'll discuss this topic in detail in storing UTF encoded text with strings in Chapter 8. Okay. There's the end of that 30-minute timer, so it's time for a break. BRB screen. I may or may not be continuing the stream after this. We'll see how I feel. Yeah, I'm going to end the stream here. I'm feeling like I've done enough of the streaming for tonight. So just going to end it here. Thanks for watching.